Okay, sorry, please go ahead.
Okay, great, thanks. Okay, yeah, so I'm going to talk about the trace reconstruction problem in the smoothed analysis model. So I've never given a talk on an iPad, but I've taught a class on iPad and given talk using slides. Hopefully this is of intermediate complexity. So what's a trace reconstruction problem? So it's a very basic problem in unsupervised learning. So here's the problem. There's an unknown string X, okay? So let's say it's like, 1, 0, 0, 1, 1, something like this. Okay, so this is unknown, okay? And what the algorithm has is access to random traces of X. So what is a random trace? A random trace of X is generated by deleting every bit of X, with independently with probability P. Okay, I got the spelling wrong. Independently with probability P. Okay, let's say probability delta actually. Okay, so fix some delta. Think of some delta. Let's say 0.5. Okay, so what's going on is that there's an unknown string X. Every time the string X is not known to the algorithm, but every time the algorithm presses a button, it gets a random trace of X, which is generated by deleting every bit of X independently with probability delta. Okay, so think of delta equals half. Okay, think of delta equals half, or actually, let's think of delta equals 2/3. Okay, so it's some fixed number between 0 and 1. Okay, so let's say suppose X was 1, 0, 0, 1, 0. So maybe the algorithm presses the button the first time, and maybe the trace that it gets is, let's say the first bit gets deleted, the second one does not, the third one does not, the fourth one does not, the fifth gets deleted. So the algorithm gets to see 0, 0, 1. The next time the algorithm presses another button and gets another trace. So this time maybe the first bit gets retained, the second bit gets deleted, the third bit gets deleted, and the algorithm gets 1, 1, 0. And maybe another time the first, third, and fourth, second, third, and fourth bit get deleted, and the algorithm gets 1, 0. Okay. So every time the algorithm presses a button, it gets an independent random trace. They may be of different lengths, but you know the generation process. It was obtained by deleting every bit independently with this fixed probability 2/3. Okay, and you're told what this delta is known to the algorithm, but it's not very hard to figure it out anyway. Okay, and of course the algorithm does not. Sorry, I have a question. The positions of the deleted bits are not revealed to the algorithm. So all the algorithm gets to see is this. After the deletion process happened, the algorithm gets to see a squished string. Okay, so it doesn't know which position mapped to what. So from seeing 0, 0, 1, the algorithm cannot tell whether the first 0 came from the first one, it was the second 0 in the original string or the third 0 in the original string. So it doesn't know which position got mapped to what. Okay, and the task is obvious. So the task is reconstruct X. Okay, the task is just to reconstruct it. So maybe this is a little, maybe I can use a slightly sharper thing. Okay, so the task is to just reconstruct X. Okay, so by reconstructing X, I mean that the algorithm will get many, many samples, and at some point, what it wants is a guarantee that with 90% probability it will output the true string X. Okay, and so the goal is to minimize time. Goal is to minimize sample complexity and time complexity. Okay. So of course, so first of all, it's just like, just as a simple exercise, it's easy to see that this problem has a finite sample complexity, because I can, like, if every bit is getting deleted with probability 2/3, then with probability 1/3 to the n, all the bits will be retained. And so in time 3 to the n, if I wait long enough, 3 to the n, I would see an n-bit string. And when I see an n-bit string, I know that this is the string I was waiting for. This is the whole string. So of course, like, as long as the constant deletion probability is a constant, you can always recover the original string X in exponential in n samples and exponential in n time. Okay. And the question is, can you do better than this? Okay. So trivial to achieve exponential in order n samples and time. And task is to do better. So unlike many problems here, the problem is that we do not even know the sample complexity of this problem. It's not a question directly of just finding an efficient algorithm for this problem. We do not know what is the best sample complexity for this problem. How many traces do you require to reconstruct X with, let's say, 90% probability? We do not know what the right answer is. And to just say how much we do not know what the right answer is, let me tell you the state of the art. So the best known lower bound is a paper by Zachary Chase from earlier this year, which shows that at least n to the 3/2 samples are required. Okay. And best upper bound of how many samples are required. Oh, sorry, I don't know why I'm writing that. So this is the lower bound. This is the lower bound on how many samples are definitely required. And upper bound, okay, so let me first say what was known until yesterday and what's known today. So, so there's a paper by Nazarov and Perez, and a simultaneous work by myself, Ryan O'Donnell, and Rocco Servideo. This is from 2017. These are both papers, simultaneous papers from 2017, which showed that that you can recover the best known give an upper bound on the sample complexity of exponential in n to the 1/3 upper bound. And in fact, you can achieve the same time as well. So upper bound on both sample and time complexity. Okay, so this is how big the gap is. The best known lower bound is barely superlinear. The best known upper bound is exponential in n to the 1/3. So let me update that a little bit. So yesterday evening, we got an email from Zachary Chase, and he uploaded a paper on the archive a day before, I suppose, or maybe yesterday, which achieves a sample complexity, a sample and time complexity of exponential n to the 1/5. So this is yesterday. Okay, but independent, like, you know, I mean, even with this update in the state of the art, the gap is still huge between the best known lower and the best known upper bound. Okay, so hopefully the problem setting is clear. Okay, so this problem seems like, okay, we do not even know what the best sample complexity is. Okay, and I should just mention, okay, so this is the state of the art for the worst case reconstruction problem, where X is chosen, where X is, like, you know, arbitrary. You do not have any guarantees on X. So let me just pause here for a minute and see if there are any questions. Okay, great. Okay, so let me move ahead. Okay, so given this is the state of, like, the worst case reconstruction problem, people have naturally focused on other variants. So actually going back to the first paper in theoretical computer science which considered this problem by Batu, Khanna, and McGregor, this is from 2004. So in that paper, they obtained a poly n sample and running time algorithm if X is generated uniformly at random. So the model is, if X is not arbitrary, but the process X, the string X is just a uniformly randomly chosen string X from the hypercube, from the n bit, it's a uniformly random n-bit string. Would the problem be more difficult if we do not know n? Well, actually, yeah, so John is right. Yeah, it's actually very easy to reconstruct n, because you can just look at the length of the strings, traces you're getting, that's following a binomial distribution. So you can figure out both the deletion probability and the length, because the length of the traces is following a binomial distribution. Hopefully that answered the question. So okay, so if X is generated uniformly at random, then with high probability over this process, the trace reconstruction problem, this paper from '04 showed that it has a polynomial in n sample. They gave an upper bound of polynomial in n sample and running time. Okay, so if the string is chosen uniformly at random but is not arbitrary, completely arbitrary, then the problem is substantially simpler. Or at least, I mean, maybe there's a Polyn sample and a Polyn complexity algorithm even in the worst case, but at least for the randomly chosen string, we can actually show something like this. Okay. But this was actually improved in the last couple of years. So so the state of the art here is by, I'm probably going to get the Holden, Perez, no, Pimentel, Perez, and Zhai, who I think this is from 2018, but there were updates to this paper. So 2018, they obtained that if X is chosen uniformly at random, then there is a 2 to the cube root log n samples plus linear time, so order n time algorithm. Okay, so if X is actually chosen at random, then there's in fact like a sub-polynomial sample complexity algorithm. So certainly if X is chosen uniformly at random, the problem is easier than the worst case, because in the worst case, at least we know there's an n to the 3 halves lower bound on the sample complexity. And but if the string is chosen at random, there's a sub-polynomial sample complexity and linear time algorithm. The reason you really require linear time is because even to read a trace, you require linear time. And again, just to remind you, we have fixed the deletion probability at some number, let's say 2/3. The precise value is not very relevant. So we've fixed the deletion probability. And I don't want to talk too much about these results, but just one thing is that so the algorithms so first of all, this 2 to the cube root log n samples in the for the average case problem, and the 2 to the cube root n samples for the worst case problem. So this 2 to the cube root, this is not incidental actually, in the sense this paper by Holden, Pimentel, Perez, and Zhai, it does actually use the worst case reconstruction algorithm on small strings, basically of length log n. So this is not a coincidence that the same cube root appears. But other than that, the worst case problem and the average case problem look very different. In particular, the worst case problem uses like the whole algorithm, and you'll see what kind of things are used. But the algorithm crucially relies on using very elementary, but crucially relies on using some tools from complex analysis to get the result. The average case results do actually rely on more like string alignment techniques. Okay, so there's a very, very careful analysis of string alignment techniques of how, so you basically try to get a bunch of traces and you're trying to align these strings. Okay, so it's a very different flavor of results for the worst case and the average, or rather not the flavor of results, but also techniques that are used are very different in the worst and the average case. So far so good. Any questions? Okay. Okay.
Sorry. So with this improvement to 1/5, do you also get an improvement to 1/5?
I do not know. So I do not think it's a black box thing, but it's so I don't think like the worst case routine is used as a black box in the average case thing. It's like it has to be a little robust to slight misalignments. So yeah. So but if that holds, it will probably like you will get a log into the 1/5. But like your paper appeared, I think yesterday, so I haven't even looked at it. So yeah. But probably. Okay. So now, okay. So what I'll discuss now is actually an intermediate model between worst case and average case models. Okay. So this is the okay. So now the model we will now discuss is the smoothed analysis model. Okay. So just a sentence about the smooth analysis model. So smooth analysis was introduced in a very seminal work of Spielman and Teng from early 2000s, really early 2000s. And what they were trying to do is to understand the performance of algorithms like simplex or a similar simplex or the such heuristics in practice, which had a very good performance in practice, but theoretically were supposed to take exponential time. And so they were trying to kind of formalize the statement that an algorithm like simplex works really good in practice. And so they came up with the smooth analysis model to, like, to make these such statements concrete. Okay, so this whole idea of smooth analysis is that you start with a worst case instance, but then you slightly perturb the instance. And then this is the modified so your input instance you do not assume is generated at random, and neither do you assume it's a worst case instance. Rather, what you assume is that the input instance is generated as follows. This is like the meta thing. I'll make it concrete in our case, but the meta idea is like you start with a worst case instance, and then the instance is just perturbed a little bit, whatever that perturbation means in the context of the problem. And then you ask, okay, how does my algorithm do it? What is the complexity of solving the problem on this instance? So it's like it says worst case plus perturbation. So like, if I have to make a caricature of the thing, smooth analysis is worst case plus perturbation. Okay. So in what I want to do is to now look at the trace reconstruction problem in the context of smooth analysis and understand what is the smooth, what is the, I don't know what the phrase should be, what is the smoothed complexity of the trace reconstruction problem. And why do I want to investigate this? Well, certainly we know the average case problem is easy. It has like a sub-polynomial sample complexity. The worst case problem might be easy, but we don't seem to be making any headway. So let's look at a slightly easier problem and see what we can say there. Okay. And turns out that actually it was our hope that whatever we do in this smooth complexity thing would somehow be useful for the worst case problem as well. We tried to do it for a while, but did not succeed. But yesterday, Zachary's email said that somehow our paper, not in any direct techniques, but somehow something in our paper inspired him to get this better worst case algorithm. So now, like, well, so rather than making improvements to the state of the art, I'm happy that we are inspiring others to do that. So that's also good, as long as something happens. So anyway, let's discuss the smooth analysis model. So the smooth analysis problem here would be that a string X is like a worst case string X is chosen by some adversary. Okay, you have no control on what X is. Okay. And then, but this is not the instance on which the trace reconstruction, you have to solve the trace reconstruction problem. Rather, what is done is, so actually let me call it X prime. The worst case instance is X prime, but then X is generated by a sigma perturbation of X prime, okay? So X is generated by a sigma perturbation of X prime. By a sigma perturbation, I just mean flip every bit of X prime with probability sigma independently at random. Okay, so think of sigma as a small number, maybe 1%, okay, 1 over 100. So the worst, some adversary chooses worst case X, you don't have to worry about solving the trace reconstruction there. Rather, then every bit gets flipped with probability 1 over 100. And now this is this X that you have generated like this. This is the unknown string. And now the trace reconstruction, you have to solve the trace reconstruction problem on this X. You get traces generated from, so you get access, algorithm gets access to traces of X, not X prime, just traces of X. And goal is to reconstruct X. Okay, so X prime is just, goal is to reconstruct X. So X prime is just defined, comes up in the context of the generation of the string X. X prime just comes up in that context, that's chosen by an adversary. Okay, is the model clear? Everything is exactly as before, and now you're getting traces from X and you have to reconstruct X. And our main theorem is that if the deletion rate is delta greater than delta less than 1. Of course, if everything gets deleted, you can't do anything. So if the deletion rate is delta less than 1, then there is an algorithm with, again, I'm just going to write one number. It's both the sample and the time complexity, with complexity order n to the 1 over sigma 1 minus delta log of okay, so let's just look at this thing. What is it saying? It's saying that the deletion probability, if delta is a constant bounded away from 1, then the factors of 1 minus delta are both constants. Okay, and the perturbation probability, the smaller the perturbation probability is, the larger you have to pay. Like if the perturbation probability is any constant, say 1%, and the deletion probability is anything bounded away from 1, this is polynomial time. As the perturbation probability becomes smaller and smaller, of course, you're like nearing the worst case string really. So really at once the perturbation probability becomes like 1 over n, which means you may not perturb any bit really. Then you expect it to become like a worst case problem. And indeed, at that point, you would hope that like, it would somehow match the worst case complexity. And that would have happened had we gotten a dependency of 1 over sigma to the 1/3, because then like, so this is probably not optimal in its dependence of sigma when sigma is really tiny. But once sigma is a constant, for any constant deletion rate delta, we are getting a polynomial time algorithm. So hopefully the result makes sense.
Maybe I missed something.
Sure.
When sigma is a half, this is not optimal either, right?
At sigma equals half.
Then you are just sampling a random.
At sigma, right. So you're saying even if sigma equals half, this is right. So even at sigma equals half, this is not optimal. At sigma very small, this is not optimal. This is right. No, you're absolutely right. So this is like potentially the dependence on sigma is not the right dependence. It should somehow, ideally one should be, somehow I don't, okay, let me put it like this. The algorithms which do achieve like this sub-polynomial complexity, so when sigma equals half, they look very different from the algorithm I'm going to present. The algorithm I'm going to present is going to look very much like a worst case algorithm. This is right. So sorry, there's another. Yeah, this is the sample and the time complexity. So both of them. So it's a time complexity and hence also the sample complexity. But yeah, this is no. So this is not optimal in its dependence of sigma at either the large sigma or the small sigma. This is probably like a reasonable dependence. For example, actually, I do not know why the following is not true. Maybe it is possible that when the deletion rate is, when the substitution rate, the sigma, is any constant, potentially you can achieve subpolynomial complexity and polynomial running time. I do not know why it cannot be achieved. So we are getting an upper bound on the sample complexity, which is polynomial in n, but potentially, like, we tried to understand if the average case algorithms can work in this setting. It didn't seem to work, but it is entirely plausible that one can improve on this time complexity substantially, like maybe get polylogarithmic subpolynomial dependence on n. Okay, hopefully I answered the question. Any other questions? Okay, so okay, so let me now explain how this algorithm works. So at a high level, the algorithm has two steps. Okay, sorry, the Rocco has a comment. I think the way the perturbation parameter sigma is parameterized in the paper, sigma equals 1 would correspond to the uniformly random string. Okay, so I did not copy the result properly. So it's not sigma equals half, it's sigma equals 1 would correspond. Okay, so I maybe messed up the parameter a little bit, but I think for whatever I'm going to discuss, you can just assume sigma to correspond to whatever process I described. It's not going to affect the thing. Okay, yeah, so sorry, right. But okay, still the answer is that when sigma approaches 1, it's still like at a very low and very high. This is probably not the right dependence on sigma. Okay. Now, okay, so let's see. So there are two steps in this. There are 2 steps in this algorithm. So step 1 is traces. From the traces, we will obtain a so-called subword count of x. Okay, so x is the unknown string. Okay, so now the entire process about its generation is gone, but like x was obtained by taking a worst case string x prime and then perturbing every bit independently with probability sigma. But now, so the x has been generated in that way, but now I'm describing the algorithm. So there are 2 steps in the algorithm. The first step is to show how, given the traces, we can obtain a so-called subword count of x. I'll say what the subword count phrase subword count means. And secondly, we will show how from the subword count of x, we can reconstruct x. Okay. And okay, so, and the thing I would first like to point out is that this part is a worst case guarantee. We will show how for every string x, given the, okay, so maybe like, I'll define it a little more formally, but let me just say what the subword count is. Subword count is like if I give you a string 10 and I just ask you how many times does the string 10 appear as a subword in x. So it's just the number of occurrences of 10 as a contiguous subword inside x. That's the subword count. So I can ask you the subword count of 111, the subword count of 001. So what we would be interested in is to show how from the traces I can recover subword counts of every short subword. Short subword would mean, short for us would mean roughly subwords of length log n. And then we show how, given these subword counts, given these short counts of these short subwords, meaning how many times 10 occurred, how many times 11 occurred, how many times 111 occurred, so on up to every string of length log n, how given these subword counts, you can reconstruct x. Okay, so maybe let me just say it's a short subword count of x. Okay, and then from the subword count of x, we'll reconstruct it. So the traces to short subword count of x, this is a worst case guarantee. We'll do this doesn't matter what x is. The subword count of x to reconstruct x, this is what will use the smoothed analysis guarantee. That this will use information about the fact that x was not a worst case string, but x was generated by starting with a worst case string and then perturbing every bit with probability sigma. Okay. So again, like, let me just, so this is, let me call this step 1 and let me call this step 2. So I'll first show how step 2 works and then I'll show how step 1 works. Okay. Step 2 is slightly easier to do. Step 1 would involve a little more machinery. So before I do that, let me just say what the subword count is. So a subword count Wx is the number of occurrences of W as a subword inside X. Okay. So okay. So this is what a subword count means. If a subword count is a function, so let me actually just abbreviate it as SW. SW W comma X is how many times the word W appears as a subword of X. Okay. And the first claim is for X generated in the smooth analysis model, if we are given subword counts SWWX for all W of length. Let me just write this down properly. So it's log of n over, let's say, kappa divided by sigma. Then with probability 1 minus kappa, we can reconstruct X. Okay. So with probability, if X was generated by starting with a worst case string and then perturbing every bit with probability sigma, then this probabilistic process with probability 1 minus, if I'm given all the subword counts of all strings, of all subwords, of all W's up to length, like log of n over kappa over sigma. So think of sigma as a constant and kappa also as like a constant, like 0.1. So if I'm given subword counts of all strings up to order log n, roughly speaking, we can reconstruct X. Okay, this is the first claim. Okay. Any questions about the claim? Or any questions about like the notion? I'll give the proof of the claim briefly. I'll describe the
Is there a deterministic criterion that you can give as well? I mean, is it like if X is a particular structure, then you can do it?
Yeah. Actually, the proof will the proof will give you what you really require, and then that would be that will hold with high probability. Yeah. So actually, this brings up an important point. The precise perturbation model is not very important. It's actually just like there's a deterministic criteria, and just when you perturb everything with high probability, that would hold. But really, like even if you perturb things in a slightly correlated manner, I think everything will be okay, really. So the proof is actually quite simple. Okay. So think of a worst case string. Okay. So okay, we require one notion. Okay. So a string of, so let me give it a name. Let me call this number K. Sorry, kappa and K is a little unfortunate. Let me call this rather than what's a good name for beta. Let me just call this beta. Okay. So okay. So I'll require this number length K. So I have all subword counts of all strings up to length K. Okay. Okay, so now one thing is, okay, so there's a notion of, we require a notion called a right extension and left extension. So, okay, let me just give an example, okay? Consider the string 1010, okay? Consider the string 1010 and consider string 0100, okay? So if I call the string A and I call the string B, then we will say B is a right extension of A. B is a right extension of A, meaning that if you start with a subword, if you start with a string A, okay, so this is, or you start with the subword A, which is just a string A, can you delete a bit from the left and add a bit to the right to get B? So that's called a right extension. So B is a right extension of A. Okay. Similarly, if you start with A, which is 1010, then the string 1101 is a left extension. So if this is A, this is C, then C is a left extension of A. Because you can delete a bit from the right of A and add a bit to the left of A, and you will get C. Okay, so this is the notion of right and left extension. You can you extend your left, can you extend your right? Okay, now here's the main thing. Okay, suppose you see a string, suppose you have the subword counts, you have the counts of how many times every string W of length K, length log n appears inside your unknown string X. Okay. Here's the main thing. If you look at X, suppose this is X, think of the last K bits. These last K bits may not have a right extension, in all the subword counts you have. These last K bits may not have a right extension. In the sense, if there's any string which does not have if there's any string of length, subword length K, which does not have a right extension, but still appears in X, so it Like, if there's a string W, if I tell you that there's a string W, which has a subword count of at least 1 in X, then the last k bits can be the only such subword which might appear in X, but may not have a right extension X. That's the only one which could potentially have this property. Of course, it's possible, like, if K is like, if this is 1101. So even though, like, maybe this 1101 appears somewhere else, or maybe 1100101 maybe appears here somewhere. Okay. And then it might have a right extension. But I'm saying the only subword, okay, observation, the only subword which appears in X if W is a subword which appears in X but has no right extension, that is, that any right extension of W does not appear in X, then it implies that W is the last k bits. Last k bits. Okay, hopefully that makes sense. That if you find a subword which has a count of 1 or higher, but no right extension appears with count, any right extension, or rather any right extension, the two right extensions, possible right extensions, do not appear with counts do not appear in the subword count in the list of subwords, then it's the last k bits. Okay. So this is the first observation. And the second thing is that, so you can be lucky and you can, so first observation is that with, so what you can show is that if the string was generated in the smooth analysis model, with high probability, the last k bits will indeed not have a right extension. Okay, that will indeed happen. If the string was generated in the smooth analysis model, this is a simple calculation, then you can show that with high probability, the string will indeed, the last k bits will not have a right extension. That way what the last k bits were. Okay. Now suppose you have reconstructed the last k bits. Okay. Then what should be the way to generate, like, if you have generated the last k bits, let's say, okay, how should you reconstruct, like, what is this b? What is this bit? Well, if you have figured out what the last k bits are, you can ask, is there a left extension of 110? There should be at least two. So is there a left extension of 1101? There is at least one left extension, and hopefully there isn't more than one left extension. I mean, if 0110 and 1110 are both present, then you do not know whether which bit B might be. But if there's a unique one, then you know that this is how you should extend it. Okay. So the whole point is, like, this kind of uniqueness of extensions. If the uniqueness of extensions property is there, then you can reconstruct the whole string. If you just work this out, the property that suffices for X to have, so for this extension-based algorithm to work out, is that for every I and j in 1 to n, okay, for every I and j in 1 to n, the subword xi I plus k minus 2. So this is the subword of length k minus 1 starting at I, is different from x j to j plus k minus 2. Okay. So if this property holds good, so let's call this perturb property or something, perturb property. If this holds good, that any subword of length k minus 1 appearing at any position is always distinct, then this extension-based algorithm will work out. And what you can show is that for k greater than equal to log of n over whatever I chose, beta over sigma, with probability 1 minus beta, a sigma perturbation has perturb property. Let me call this something else. Let me call this property P. Has property P. So this is the precise property you require for the extension-based algorithm to work. Hopefully that made sense. Did I answer your question, Joe? Like this is the deterministic property you require, that all subwords starting at any position of length log n, roughly speaking log n, should appear distinct. As long as that happens, you can reconstruct the string. But you can reconstruct the string provided you have the subword counts. The question is, how do you have the subword counts? You are given traces. How do you figure out how many times a subword appears? Okay. So this was the part which required the smooth analysis idea. So now claim 2, or rather which was claim 1, is from traces of x, we can infer subwords of x of short length, of length log n. So let me just call it k. Okay. So now let's think about the following problem. Let's think about the following problem. You are getting access to traces of x. Since you want to recover the subword counts of all subword counts for all subwords of length k, and k is roughly log n, you can just do it one at a time because there are only 2 to the k possible subwords. There are only 2 to the k possible strings. So you can iterate over all of them. Okay, so just think about the following problem. You have an unknown string x, you're getting traces from x, and now you want to recover how many times does the string subword 00000 of length k appear in this x. How many times does 00001 appear there? How many times does 002 or 0010 appear? You can iterate over all such strings, and you can iterate over all strings of length k, and then you will have the entire subword count for x of length up to k. This is just a 2 to the k factor overhead, but k for us is like log n, so this is not a big deal. So the question really becomes, goal from traces of x, recover SWXW. SWXW just means how many times does the word W appear as a contiguous subword in X. Okay. And the most obvious thing one can do here is the most obvious thing to try is the following. It is this, that, okay, you're getting traces of X. Okay, so you can just count how many times does the word subword W appear as a word in the trace of X. Now, of course, here's the issue. Maybe like, if this is the string X, okay, and I just want to count how many times I get a trace of X. So maybe I get the trace, which is 11011. Okay, so maybe only the second bit got deleted. Okay. Now, of course, the first 11 doesn't correspond to a true subword, because the first 11 in the trace corresponds to a 101 where the 0 got deleted. But the latter 11 corresponds to a true subword which appeared in the original string that got retained as a subword in the trace as well. So if we want to count like contiguous subwords and traces, they are outcome of subwords from the original string X, but also outcomes of perturbations, outcomes of deletions, like things which came as a result of deletions. Okay, so if you just do this thing, how many times does if I just think about how many times a string subword W appear in a trace of X, what's the expected number of times it will appear? Well, if the subword W appears in X, call it SWXW times, okay, then it will get mapped as a subword in the trace with probability 1 minus delta to the k, because all those bits need to get retained. Then there are subwords which are, then there are subsequences in X which upon one deletion become a subword. So if I call that SW, so let me call it SW0, SW1XW. SW1XW just means these are subsequences in X which after one deletion look like W. W. Well, that would be 1 minus delta to the k times delta, because that one bit in the right position needs to get deleted and everything else needs to get retained. So on and so forth. I think n minus k really. This is what you're getting, okay? So this is the expected number of subwords, expected number of subwords W in a trace of X. And what you're interested in is this quantity. Okay. Now this is the expected number. So you may not be able to count this expectation exactly. This is the main issue, that you are not able to count this. Okay. So first of all, there are two. Okay. So how much time do I have left?
Becky, how much time?
Oh, I mean, it's, I think, how much time do you need?
I don't know, 10 minutes, 5 minutes, I don't know, 10 minutes.
Oh, you definitely have 10 minutes.
Okay, okay, sounds good, okay. Okay, okay. So let's try to understand what's going on, okay. We of course have an easy empirical estimator for the expected number of subwords of W in a trace of X, right? I can just sample a trace, see whether W appears or not. I can sample another trace, see whether how many times W appears there or not. So I have an empirical estimator for the right-hand side. The question is, how accurately do I need this number? Okay, because I know this equation is true. Okay, okay. So let's. Okay, sorry. Maybe I should say one more thing here. It would be I can divide this thing. I can divide this thing, and oops, sorry. I can divide this thing and get that summation SWJ XW delta to the J equals expected number of subword W in a trace of X. So this is a quantity which we do not have exactly, but we can have an empirical estimator, divided by 1 minus delta to the K. Okay, so I just divided everything by 1 minus delta to the K, and I have this equation that summation SWJ XW times delta to the J equals expected number of subword W in a trace of X divided by 1 minus delta to the K. I have an empirical estimator for the numerator here. And remember, what I'm interested in is SW XW. SW, not XW. Okay. Now, second observation is, so this is one thing. Well, maybe this is observation number 3. I've used second observation too many times. Observation number 3 is that because I have traces from a deletion channel with probability delta, I can simulate traces from a deletion channel with delta more than delta prime more than delta, right? I can delete my bits on my own. I'm saying that it's not just the case that I have traces from a deletion channel with deletion rate delta. I have traces from a deletion channel with deletion rate greater than delta as well, if I so choose. And this is crucial. Okay. Now pretend, suppose I did not have this, this number, expected number of subwords W in a trace of X. I have an empirical estimator for that. But if instead of an empirical estimator, somebody actually gave me the exact number, then that would have been great. Why? So let me call this something. Let me give it a name. Let me call this PWX delta. Okay. Suppose I have an empirical estimator for the quantity PWX delta, but suppose somebody gave me the value. Well, then this would be great, because observation 3, simulate from channel. Okay, we can simulate from channel delta prime greater than delta. Okay, we can simulate traces from channel with delta prime greater than delta. Well, why is this great? Because see, Now I want to, I have a polynomial on the left-hand side, right? I can call this, actually, let me not call this PW. Let me call this AW because I want to call this as a polynomial. This I can call this as a polynomial. This I just defined this polynomial to be P delta. This is a polynomial in delta. Okay. So now this is simple. So let me just explain this in words really rather than writing. I have a polynomial P delta, which I've symbolically defined here. I am interested in its constant coefficient. That's what I care about to know. SW0XW, that is the constant coefficient in delta. That's the coefficient which does not depend on delta. What I have on the, suppose I got the exact values of AWX delta. Well, then I have evaluation of P delta. We observe that we can simulate values of, I can also get P delta prime for delta prime greater than delta. So if I had the exact values, if I had the, if I had the exact values, then I could have just done the polynomial interpolation, right? I have the value of P delta. I will compute P delta plus ever so larger, slightly larger number, then another larger number, then another larger number. This is a degree n equation. I'll get n different values. I'll do polynomial interpolation to figure out the constant coefficient. I still plan to do that. The only issue is that I do not have AWX delta exactly. I only have an empirical estimator for AWX delta. So the question really becomes, how well do I need to figure out the value of AWX delta so that the polynomial interpolation can work out properly? That's the main question. If I want to know the constant coefficient in P delta, I do not have the exact evaluations of if P delta equals AWX delta divided by 1 minus delta to the K. I do not have the value of AWX delta. I have an empirical estimator for that. So I want to know how well do I need to figure these numbers out, the numerator out, so as to recover the constant coefficient P delta. And what we want to not do here is we do not just want to apply some black box thing. Okay. We want to be a little careful. Okay. So now the question really becomes the following. Okay. Forget about the computational complexity of this problem. That's like, we can make it efficient very easily. This is not a big deal. Here is the issue. I have an unknown polynomial P delta. I know all its coefficients are integers. Okay. I have a polynomial P, okay, given polynomial P. Okay. I have a polynomial P, as in I don't have access to it, but I can evaluate it at P delta, and I can evaluate it at P delta. I can evaluate it at P delta and P delta prime for any delta prime greater than delta up to 1. That's the maximum value of deletion rate. Okay. But I can only evaluate it to some error, namely to can evaluate P to error plus minus epsilon in the interval delta to 1 at the cost 1 over epsilon squared, that's like the empirical estimator thing, times 1 over 1 minus delta to the K. Goal, recover P0. And information that we have is P has integer coefficients and if you look at the second thing that you know is that if you look at the sum of all the coefficients of P, okay, so I'm just denoting it by the L1 norm of P, it just means the sum of all the coefficients of P, that is at most n to the K. So again, like, think of this as n to the log n. So the way I'm describing the algorithm, you'll get an n to the log n time algorithm. That's like n to the log n, but this can be made better. Okay. So, okay, I'll wrap this up in a few minutes now. So P has integer coefficients. So here's the problem. You have a polynomial P, you know it has integer coefficients. You want to recover the constant coefficients. So this is the thing we want to really leverage. That is the integer coefficients only. you can evaluate it in any interval. You can evaluate it in the interval delta to 1. But to you don't have an exact evaluation oracle. To evaluate it to error epsilon, you will pay a cost of 1 over epsilon square times 1 minus delta to the k. K is again like log n. So really the cost is like 1 over epsilon square. You want to know how accurately do you want to evaluate it, this polynomial p in the interval delta to 1, so that you can evaluate from that, recover what the constant coefficient of p is, or p0 is, but you want to leverage the fact that p only has integer coefficients. So if you, again, ignore time complexity for the moment, what is the question you really need to know? That can there be two different integer coefficient polynomials such that their constant coefficients are different, but they're and their L1 norms are at most n to the log n, but they're both they're almost like, super close in the interval delta to 1. Could it happen that there are two different integer coefficient polynomials p and q? Their constant coefficients are different. P0 is not equal to Q0, and yet in the interval delta to 1, they're super close to each other. Because if that is the case, then just by getting noisy evaluations of P in the interval delta to 1, you cannot figure out what the constant coefficient of P is. And the answer turns out to be, so this is the main claim. So you can subtract these two polynomials. So this is the main technical claim. If P and Q are integer coef polynomials, integer coefficient polynomials, P0 is not equal to Q0, meaning the constant coefficients are different. The L1 norm of P and Q are both bounded by n to the k. Okay. Then P minus Q in the interval from delta to 1 must, at some point, there must be a point where they differ by, let me just record this properly. It is at least n to the minus k over 1 minus delta. Meaning that if P and Q are integer coefficient polynomials whose constant coefficients are different, then, and the L1 norms are bounded by n to the k, as is the case with the polynomial we care about, then if you if you get the evaluations up to granularity n to the minus n, up to error n to the minus k over 1 minus delta, then, and think of k again as log n, so this is like, and delta is a constant, so it's like quasi polynomial in n, then you can uniquely figure out what the constant coefficient of p is. And this claim, basically, like after a couple of lines of arithmetic, this tells you that in sample complexity n to the order k over 1 minus delta, you can recover the subword count xw for w of length k. So for us, k is like log n. So this will give you n to the log n time algorithm. You can make this a little, do a few more tricks, and you can get it down to polynomial in n. I am almost out of time. So let me just say one thing. I did not get to the most interesting part, really. The claim, this claim that this is a claim about real valued polynomials, integer polynomials on the real interval. But the way you actually prove it is actually a very standard recipe of like proving such lower bounds for extremal valued polynomials. So you basically have to use some complex analysis to prove this. And what you would really be leveraging is that the polynomial p minus q, its L1 norm is bounded. Its constant coefficient is at least 1 because they're integers, and if they're different coefficients, they're at least 1. So you can just look at the polynomial p minus q, and you will just really use two properties. Namely, on the entire unit circle, it will always remain bounded because its L1 norm of coefficients is bounded. And yet the polynomial p minus q at the origin takes a decently large value. It's at least 1 because it's p0 minus q0. You can just use then a little bit of three-circle theorems and stuff to prove this claim, really. And from there, the whole thing follows. I am out of time now, definitely. So let me stop and I can explain any parts, any questions. Yeah.
Great, thanks. Are there questions, additional questions to Anindya? Okay, I have one.
Yeah.
So I didn't quite get it, but if I give you a distribution that conditioned on all the other bits, this particular bit has at least sigma probability to be both 0 and 1. Is this enough to push through your result?
I think so. Yes. Yes, I think so. So yeah, like if you it's yeah, that is enough. Like if you just you do not require them to be independent. You just need that.
You just want some, you just still want some randomness conditioned on what happens.
Yeah, yeah. You just want some randomness to be there. So there's another question: how does sigma factor in? Right. So the sigma, the k. I said the k is log n, but the k is actually like, log n over sigma. So if you want to think about the running time, it's like it will right now the way I've written it will be n to the log n over sigma, but it can change it and you can make it n to the 1 over sigma. So that requires a little more work.
Maybe because your method is so general, that's why you don't achieve what happens in the uniform bit case, right?
Yeah, yeah. Yeah. I mean, the algorithm. The clever part of the algorithm was, I mean, okay, sorry. So rather the first part of the algorithm was the only part, which was one part of the algorithm, forget which one I said first. The one part of the algorithm was completely for worst case strings, to go from traces to subword counts. That's true for anything you can go. The question is, how are subword counts useful? And for strings which were generated at random, or strings which are generated by this perturbation model, it turns out to be useful. And it seems somehow that actually what we're hoping turns out to be true. So this paper I alluded to in the beginning by Zachary Chase, so he uses subword counts of a worst case string x to reconstruct x in a clever manner than the earlier papers did. So yeah, so this is not really using the random structure too much, whereas the previous algorithms which got like subpolynomial complexity, they really used the fact that x was randomly chosen. There was like a lot of yeah, I guess random walk action going on there. So
great. Oh, there's another question coming.
Yeah, can you repeat the part why p minus q has a lower bound? Right. So okay, so p and q are integer coefficient polynomials. Okay, so maybe I can just say this again. So think of the polynomial p minus q as r. Okay, r has integer coefficients. Why? Because, well, p and q do. We are thinking of the case when p0 is not equal to q0. So r0 is actually also r0 is 1 or -1 or 2 or -2. Important thing is r0 is also at least 1. And the final thing is that the L1 norm of r is at most the L1 norm of p plus the L1 norm of q. So that's also n to the k. Okay. And now what we are interested in is if you have such a polynomial r and now you look at the interval delta to 1. So think of delta as 2/3, okay? We want to know what is the minimum value r can take in this interval under these conditions, okay? And maybe let me put it like this, okay? If you look at the complex circle like this, okay, because r is a non-zero polynomial with constant coefficient, the constant coefficient is not irrelevant as such. Because r is a non-zero, r has at least like the square of the coefficients of r is at least something, is at least 1, because like the first thing is value 1. It's obvious to prove, like a one line of arithmetic shows that r must take a decently, the average value of r on the unit circle must be large. That's just because r has non-zero coefficients. is that the one coefficient is 1. So the average value of the norm of RZ square when Z is chosen from the unit circle is at least 1, if Z is chosen from the unit circle. And what we are now, and on the other hand, I also know that at the here, R0 is always also at least 1. So it's a polynomial which has a large value on the periphery on an average. This is a polynomial which has a large value at the center. And the third thing is that this is a polynomial which cannot be super large anywhere in the unit disk because its L1 norm of coefficients is n to the k. So its value in anywhere in the unit circle cannot exceed n to the k. Such a polynomial, and for that matter, such a analytic function really, has to be somewhat large here. This is just basically, if you want to apply, you have to apply the 3-circle theorem on 3 concentric circles. This line segment can be transformed into a circle after the right map. And you will get that this R cannot be super tiny on this thing. It has to be at least n to the minus k over 1 minus delta. I can show the proof, but that will take a few more, like 10 more minutes to show the proof of why this is true.
I have a question, which is kind of following up on the previous questions, which is that there's another way you could potentially relax the worst case model, which is to ask for an approximation algorithm. So you start with the worst case traces, and then you don't want to reconstruct exactly, but somehow approximately. So one natural thing could be to approximate up to edit distance something relatively small. So I guess in the 2 steps of the proofs, one is just would work for worst case. And I guess the question is, can you go from the subword counts to reconstructing approximately for even worse case?
Good. Right. I think we thought about it, but we did not have any answers. But maybe now, in light of Zachary's paper, I should again think about it. I think we thought about, like, what can be done in the worst case. Definitely thought about maybe, like, there's a approximate edit distance, something can be done. Yeah, we didn't make any headway on the worst case reconstruction. But yeah, this is a good question. Yeah, this is a very valid question. Can we do something like edit distance thing?
Thanks. I also have another kind of different question, which is, can you do insertions as well? Because it seems like you just have to modify these polynomials and it could potentially work.
You wanted to? Yeah, I mean,
it's not the deletion channel, but you also have insertions.
Okay, the deletions, I think it should work. I mean, the first worst case reconstruction papers, those did have deletion, and actually sometimes those also had insertions. And the funny thing was sometimes insertions made the problem easier. At the right level of insertions, it was like helping things. So yeah, maybe it should work out. I do not know, but yeah, I would suspect yes, but I do not know the proof. I haven't thought about it. Yeah, possibly yes.
Thanks.
Great. Are there other questions?
Hey, Anindya. Can you hear me?
Yeah,
so,
yeah, I can hear you.
I'm just wondering, it's really cool, like this, looking at the polynomial with respect to delta, but I'm just wondering, did you try to do the more obvious thing than that, which is just to consider the linear operator where, the rows are indexed by all words of length like log n, and the columns are indexed by all of their subwords. And, the entry is just the probability to get one from the other after deletion. So you basically want to just invert this linear operator, right?
Right.
And I mean, it seems plausible that, maybe one can calculate the condition number of this operator.
So no, that's a very valid question. So not for this one, we did not try, but usually, yeah. So I think this is you write out the linear operator and just try to invert it. But I think, I do not know if we tried it for this one, but we definitely have thought about similar statistics. Here we are looking at subword statistics. You can construct the linear operator for other statistics like subsequences or so on. The condition number of this tends to be pretty bad. So you really kind of use
exponentially bad?
exponentially bad, exponentially bad. It's usually all these, the linear operators, if you just try to invert it as a linear operator, it doesn't, like, it's exponentially bad and you do not manage to get anything. It actually crucially uses the fact that you're not trying to invert it on an arbitrary thing, but something where, like, the vector in question has some nice structure. Rocco gave I think the examples where the subword count doesn't specify the string up to a, okay, so yeah, I think he's saying that if this were, sorry, I think Rocco was saying something about the previous question. Sorry.
Question, yeah.
Okay, so no, sorry. So coming back to the question, yeah, no, it's a very natural approach to try, but
so you're saying like there's something which is very close to the kernel, but it doesn't meet 0-1 strings. That's like,
it doesn't meet 0-1 strings. It doesn't meet 0-1 strings,
and that's also okay. Actually,
yeah.
Nice.
Yeah, actually, so this like, this basic idea of, like, trying to understand how these polynomials with restricted integer coefficients will behave and trying to invert them in, like, context of these kind of noisy reconstruction problems. So this has been around in several papers for the last few years. And I think the earlier papers made a point there that if you just try to write out the linear operator, even for other, like, seemingly similar problems, but not exactly the same problems, the linear operator usually has a very poor condition number. So you have to kind of use the vector on which you're trying to invert.
Okay, so Rocco, do you want to answer Mika's question directly?
Yeah, there's not much to say on it, just that I think there are fairly simple examples where you can have one string with a particular multi-set of subwords and another string which is pretty different from it, has large edit distance, but has the same multi-set of short subwords. So, like, if you imagine a block of zeros, a block of ones, a block of zeros, the subword, multi-set of subwords is going to look the same for that kind of no matter where the block of ones is. So I think this, yeah.
Okay, great. Are there additional questions or comments? Okay, let's, René, you want to say something?
Yeah, I wanted to ask a really quick question. Like, there's the first claim you proved, which I think you called claim 2, which is like take the subword count and reconstruct the thing. It seems like it seems related to those shotgun reconstructions. I guess Joe knows about it much more than me, but I'm wondering if, like, you can use,
I think Mickey
all
is
those.
probably more the expert on that.
Ah, right, Mickey's here too. So yeah, Joe and Mickey. So I'm wondering if you can use one of these as a black box. Maybe to like replace, like, your technique and then get something more stable.
I have heard of the name shotgun sequencing, but I do not know what the problem is precisely. So I don't know, maybe one of you can answer. Like, I do not know actually what the, like, does it, I don't know if it, like, it might be, but I don't know. Yeah, sorry, I don't know the exact question though.
So does Mickey or Joe want to say something?
Yeah, I don't know if it can be replaced by a black box, but yeah, I can certainly send some references that are relevant.
Very great.
Okay, they seem to have to think about it. Any other comments or questions? If not, let's thank Anindya again for a very nice talk. Guess that's it for today, and see you next time.
Thanks.